Spectroscopic and Computational Analysis of 4-methoxythioanisole. K. Jayakumar, D. Nandhini, S. Subashchandrabose Center for Research and Development, Prist Deemed University, Volum, Tanjavur, 613,403. Abstract. In this work, a joint experimental and theoretical study on 4-methoxythioanisole, 4-MTA, is reported. Detailed analysis of the FT-Raman, FTIR, and Nmr spectra of 4-MTA has been performed. In parallel, quantum chemical calculations based on DFT, B3LYP, methods were used to determine the geometrical, energetic, and vibrational characteristics of the molecule, and complete assignments were performed on basis of the analysis of the potential energy distribution, PED, of the normal modes. The theoretical spectra were refined using scaled quantum mechanics force field, SQM-FF, method as well as the uniform scaling approach. NBO analysis was applied to understand the intramolecular hyperconjugative interactions between bonding and anti-bonding orbital. The Mulliken population analysis on atomic as well as on the NBO charges, and the HOMO-LUMO energy are calculated. Besides the molecular electrostatic potential, MEP, thermodynamic properties are also reported. 1.introduction. In the past, anisole has been investigated as a key molecule for the description of a number of molecular properties due to the possibility of torsion of the methoxy group with respect to the aromatic ring. Anisole was taken as the parent molecule for reference in a systematic study on dissubstituted aromatic molecules 1, 2, and more recently it has been considered as a model system for the study of intermolecular interactions due to the presence of the polar methoxy group. This group is able to form hydrogen-bonded networks, due to the non-bonding electron density at the oxygen atom, but only as a proton acceptor. There is the possibility of obtaining detailed information from these complexes about both intermolecular interaction and the dynamics of chemical reactions. 3. Anisole, anisic acid, and their derivatives are widely used in chemical reaction as intermediates to obtain target materials such as dyes, pharmaceuticals, perfumes, photoinitiators and agrochemicals. Spectroscopic investigation of anisole 4, 5, and its derivatives has received considerable attention as the former is a representative model compound for a number of chemically and biologically interesting systems. Many attempts have been made to study the various types of spectra arising from anisole and its substituents. Calculation of the structures, stabilities, and vibrational spectra of arsenates, thioarsenites and thioarsenates in aqueous solution was performed by Tassel et al. 6. Mariko et al. 7 studied the molecular structure of jet-cooled thioanisole by laser-induced fluorescence spectroscopy and of initio calculations. Vibrational analysis and theoretical calculations of p-methylanisole in the first electronically excited S1 and ionic ground-due states were carried out by Gianu et al. 8. Krishnakumar et al. 9 reported the scaled quantum chemical studies of the structure and vibrational spectra of 2-methylthio, benzimidazole. The rotational isomerism of anisole and thioanisole was investigated by Mario et al. 10 on the basis of computational methods within the framework of the Moller-Plesset and density functional theory. Venkatram et al. 11 studied the transferable valence force fields for substituted benzenes, and vibrational analysis of substituted anisole was carried out by Lakshmaya et al. 12. A Raman spectroscopic study of the low-frequency vibrations in anisole D5 and anisole D8 is conducted by Tialai et al. 13. The literature survey reveals that thioanisole and its derivatives have attracted many researchers. In this work we report the FTIR, FT-Raman, and Nmr spectral analysis of 4-MTA utilizing DFT, B3LYP. Vibrational spectral analysis has been done using B3LYP with several basis sets. The band's assignment is based on PED. The minimum energy conformational analysis was carried out with the help of potential energy surface scan. The redistribution of electron density, ED, in various bonding and antibonding orbitals and E2 energies has been calculated by natural bond orbital, NBO, analysis using the DFT method to give clear evidence of stabilization originating from the hyperconjugation of various intramolecular interactions. HOMO and LUMO analysis has been used to elucidate information regarding charge transfer within the molecule. Furthermore, the electric dipole moment TOT, isotropic polarizability at HOT, finite hyperpolarizability STO, and also the molecular electrostatic potential, MEP, for the tidal molecule are also evaluated from the computational process. 2 experimental details. The compound 4-MTA in the liquid form was purchased from Sigma Aldrich Chemical Company, USA, with a stated purity greater than 98% and was used as such without further purification. The FT-Raman spectrum of 4-MTA was recorded using the 1064 nanometers line of a ND-YAG laser as excitation wavelength in the region 103500 cm1 on a Bruker model RFS 100/S spectrophotometer. The FT-IR spectrum of this compound was recorded in the region 400-4000 cm1 on an IF66V spectrophotometer using NaCl cell and standard GES detector. The spectra were recorded at room temperature, with a scanning speed of 10 cm1 per minute and at the spectral resolution of 2.0 cm1. The theoretically predicted scaled IR and Raman spectra at B3LYP/6-311/6-311++ G, level of calculations along with experimental FT-IR and FT-Raman spectra are shown in Figs. 1 and 2. Nmr spectra were also measured in DMSO at ambient temperature on a Varian mercury VXBB 300 spectrometer, 299.95 MHz for 1 hour and 75.43 MHz for 13C. The FT-IR and FT-Raman spectral measurements were carried out at Sri Chitra Tirunal Institute for Medical Sciences and Technology, Thiruvananthapuram, Kerala, and Nmr is taken from RSIC, IIT, Chennai. 3 computational details. For meeting the requirements of both accuracy and computing economy, theoretical methods and basis sets should be considered. DFT has proved to be extremely useful in treating electronic structure of molecules. The density functional 3-parameter hybrid model, DFT/B3LYP, at several basis set levels was adopted to calculate the properties of the studied molecule. All the calculations were performed using the Gaussian 03W and Gaussian 09 Riva.02 program packages 14 with the default convergence criteria without any symmetry constraints 15. The energetically minimal geometry was taken from the P-scan computations, described below, and the starting geometry has been further optimized at each level of theory. Vibrational analysis confirmed that all the structures studied in this work were true minima on Ps, since no imaginary frequencies were observed. 3.1 Potential energy scan. When neglecting the methyl groups, due to their very low energy barrier for reorientation which is normally present even in the solid state, the conformational problem of 4-MTA may be strictly related only to the orientation of the substituents. The two-dimensional relaxed potential energy surface scan, using internal redundant coordinates, through the opt=mod redundant option, has been performed for the angle C12S11 C1 C6 and C5 C4 016 C17 at the B3LYP/631 G, D, level of theory, using Gaussian 09. The initial geometry was symmetrized, assuming the ideal symmetry of the phenyl ring, and the relaxed scan was performed at every 30.0 degrees in the range of 0.0 to 360.0 degrees for each angle. The resulting grid including 169 points is plotted in Fig. 3. The energy values for each point were recounted into kJ/mol with respect to the lowest energy grid point. The P-scan clearly reveals that the only stable conformation corresponds to the sharp, ISO energetic minima. The minima define the orientation of CH3SPH and CH3OPH groups to be, respectively, almost ideally perpendicular and parallel with respect to the phenyl ring plane. The 4 minima correspond to the stable conformers which are however energetically degenerated and equivalent by the local symmetry. As a result, the corresponding spectra are undistinguishable. The energy barriers for the rotation over SPH and OPH bonds may be estimated by B3LYP/631G, D, as 3.2 and 14.4 kJ/mol, respectively. Such a low energy barrier for the rotation about the CS bond may suggest that the deformation of this molecular part may be easily expected in the solid state, especially taking into account the occurrence of pp stacking interactions. Since there is no hydrogen bonding expected in the studied system, which is rather mainly driven by London forces, we can compare this energy barrier with the kT value at standard conditions, which may be estimated as 2.48 kJ/mol. Although the applied theory level is not of the highest quality, and the approximation is straightforward, it suggests that the reorientation disorder of this molecular fragment may be present at room temperature. The results might suggest that such disorder plays a crucial role in the crystal melting, which occurs just below the room temperature, 22 to 23 OC. In comparison, it is much lower than 4 MTA, which melts Ca 56 to 60 OC. This difference is also shown by the computed energy barrier for the rotation about the CO bond, which is also much higher. 3.2 Vibrational Analysis. B3LYP at several double and triple dash. Basis set levels has been applied to study the theoretical vibrational spectrum of 4 MTA. A detailed description of vibrational modes can be given by means of normal coordinate analysis, NCA. NCA analysis based on the SQM-FF method was performed using MALVIBE program Ver. 716, 17 written by T. Sundias, delivering the potential energy distribution contributions of each normal mode, their corrected frequencies and the recomputed infrared and Raman intensities after scaling of the force field. For this purpose, the full set of 68 standard internal valence coordinates, containing 14 redundancies, has been defined as given in Table Point 1. From these, a non-redundant set of local internal coordinates was constructed, Table Point 2, much like the natural internal coordinates recommended by Fogarasi and Pulley 18, 19, 20. The theoretically calculated DFT force.elds were transformed to this latter set of vibrational coordinates and used in all subsequent calculations. The SQM calculations were performed based on the Pulley's method, according to which the internal force constants are transformed according to geometric mean scaling. 2 Experimental details. 1, 2. Experimental details. Where SI denotes a scaling constant. In the application of the method, the non-diagonal terms in the potential energy depend nonlinearly on the scale factors. The MALVIBE scale equals 1 option has been chosen, what means that the factor that occurs in front of the non-diagonal force constant is .xed during the iteration. The SQM adjusted Raman activities, AI, were then transformed into the Raman intensities, 2, using the relationship derived from the theory of Raman scattering 21. 2. Where is the exciting wave number? In CM1, the SQM corrected frequency of the ith normal mode, Hc and K are the fundamental constants, and is the temperature, 298 K, F is a suitably chosen common scaling factor for all the peak intensities. The SQM-FF vibrational analysis with B3LYP was performed at the following basis set levels: 631 G, D, 631 plus G, D, 6-311 plus G, dP, and 6-311 plus G, dP. The applied sets of transferable scale factors were taken from the literature without further refinement, except of 6-311 plus G, dP. V. Krishnakumar refined the classic Pulley-Rallrhut 631 G, D, scale factors 22, which were also applied here, for the triple dash quality force fields, and has shown the very good agreement for the calculations with an analogous compound 23. R. Korlacki has also proved that the scale factors refined for B3LYP/631 plus G, D, work extremely well for very large, liquid crystalline polyatomic thiobenzoates 24 in the case of 6-311 plus G, dP, basis set, the quoted Pulley-Rallrhut 631 G, D, Scale factors were refined with respect to the assigned experimental bands. Since the experimental spectra are not very rich in bands, most of the similar coordinates were grouped together and finally 7 scale factors were chosen for refinement. The error of one scale factor connected with some of the Tors ions was rather high, so the torsional coordinates were further combined and finally, the total number of scale factors was reduced to 6. In the case of 6-311 plus G, dp, and 6-311 plus G, dp, the uniform scaling factor of 0.9679, which was suggested for the computations at the quoted levels, has also been applied for comparison. 25 The PED was calculated for the scaled force field obtained with B3LYP/6-311 plus G, dp, theory level, and the experimental results were interpreted on the basis of these results. All the computed wave numbers were collected together and presented in table.S1 along with calculated root mean square deviation values, RMSD, PED contributions for each normal mode, and the band assignment. 3.3 Hyperpolarizability calculations. The first hyperpolarizabilities, SS, A0 and .A, of 4 MTA were calculated at the B3LYP/631G, dp, level, based on the finite field approach. In the presence of an applied electric field, the energy of a system is a function of the electric field. First hyperpolarizability is a third-rank tensor that can be described by a 3x3x3 matrix. The 27 components of the 3D matrix can be reduced to 10 components due to Kleinman symmetry 26. It can be given in the lower tetrahedral format. It is obvious that the lower part of the 3x3x3 matrices is a tetrahedral. The components of SS are defined as the coefficients in the Taylor series expansion of the energy in the external electric field. When the external electric field is weak and homogeneous, this expansion becomes 3. Where is the energy of the unperturbed molecules, is the field at the origin, and are the components of the dipole moment, polarizability, and the first hyperpolarizabilities, respectively. The total static dipole moment, the mean polarizability, the anisotropy of polarizability, and the mean first hyperpolarizability, using the x, y, z components are defined as the total molecular dipole moment, and mean first hyperpolarizability, are given in table. 3 and equal 1.0402 dBi and 3.1300 x 10 to 30 isu, respectively. The total dipole moment is approximately equal and the first hyperpolarizability of the tidal molecule is 8 times greater than that of urea, and SS of urea are 1.3732 dBi and 0.3728 x 10 to 30. For results and discussion. 4.1 Molecular geometry. The optimized geometrical parameters of the tidal molecule are given in the table. S2 using B3LYP/6-311G, dp, /6-311 plus G, dp, methods. The optimized molecular structure of 4 MTA is shown in Fig. 4 with the atom numbering adopted in this work. Since the exact molecular structure of the compound is not available, the calculated geometry of 4 MTA is compared with available gas electron diffraction data of thioanisole 27. From the table. S1 it is evident that the electron donating tendency of sulfur influences the bond length as well as the bond angle values. The optimized bond length of C1s11 in 4 MTA is 1.795 and 1.785 A by B3LYP 6-311/6-311 plus G, dp, and HF, 6-311 plus G, dp, respectively. On the other hand, from gas electron diffraction data of thioanisole the C1s11 bond length is predicted as 1.813 A, which deviates by 0.028 A from the theoretical value. The bond angles of the six-membered carbon ring are usually less than or equal to 120 degrees. In the present investigation, the optimized bond angle of 4 MTA is obtained at 120.7 degrees for C1, C2, C3 and C1, C6, C5, while the C2, C1s11 bond angle is obtained as 120.5 degrees. The bond parameters calculated by the theoretical methods are more or less equal to the available experimental data. 4.2 Vibrational Assignment. The total number of atoms in this molecule is 20, which give 54, 3 and 6, normal modes. The molecule belongs to the C1 point group, thus all the 54 fundamental vibrations are by definition both IR and Raman active. The vibrational spectral analysis has been carried out on basis of the FT-IR, FT-Raman measurements in combination with the computed vibrational frequencies. Vibrational mode assignments have been made on the basis of the relative intensities, the wave numbers, and PED contributions. A good correlation was found between the computed and the experimental spectra, which confirms that no significant specific interactions may be found in the studied system. The calculated vibrational wave numbers, measured FT-IR and FT-Raman band positions, and the calculated PEDs for each normal mode are presented in table.s1. Experimental frequencies are compared with all the theoretical wave numbers delivered by previously mentioned procedure. The presented PEDs obtained for the SQM scaled force fields were derived from B3LYP/6-311++G, dP, computations, where the scale factors were refined with respect to the present experiment. As may be seen in the table, the application of SQM gives certainly better results than the simple uniform frequency scaling. However, the SC stretching frequency has been predicted poorly by the quoted level, what increases the estimated RMSD. Moreover, the further refinement might bring even better improvement, but since the recorded data are not rich in bands and the Raman spectrum is quite noisy, it would not be possible to construct a more complex set of scale factors. The experimental spectra are plotted versus the quoted theory level in Figs. 1 and 2. All the computations delivered very similar intensity relations. Application of SQM had also negligible influence on the calculated PEDs, which were derived from the B3LYP/6-311++G, dP, results. The whole discussion presented below is based on the quoted SQM theory level. For the better understanding, vibrational modes have been discussed under separate headings, viz. CH vibrations, ring vibrations, CH3 vibrations, CO vibrations, and CS vibrations. 4.2.1 CH vibrations. Aromatic compounds commonly exhibit multiple weak bands in the region 3100-3000 cm1 due to aromatic CH stretching vibrations 28. Our title compound 4-MTA has one aromatic ring as shown in Fig. 4. The scaled vibrations, modes, 54 to 52, which are assigned to aromatic CH stretching, and computed in the range 3050-3077 cm1 show good agreement with the recorded very weak FT-IR line at 3080 cm1 and strong FT-Raman line at 3081 cm1. As expected, these four modes are pure stretching modes, as it is evident from the PED column. Their contribution from CH stretch is close to 100%. Although the computations were performed in harmonic approximation, the application of SQM delivered a partial compensation of the errors given by simplified vibrational approach. In the benzene ring, the CH in-plane bending vibrations most often lay in the region 1239-70 cm128. In 4-MTA, the band of medium strong intensity, observed in the FT-IR spectrum at 1290 cm1, as well as the weak one at 1106 cm1 were assigned to the CH in-plane bending vibrations, strongly mixed with the C-car stretching modes. The former mode manifests also as a weak band in the Raman spectrum. The most intensive band in the FT-IR spectrum at 1504 cm1 is also related to the in-plane bending vibration, 48% in PED, significantly coupled with the ring stretching vibration, 33% in PED. The bands observed at 826 and 805 cm1 in FT-IR are assigned to CH out-of-plane bending vibrations. These assignments show good agreement with theoretically scaled harmonic wave number values at 829 and 803 cm1. 4.2.2 Ring vibrations. Several ring vibrations are affected by substitution to the aromatic ring of benzene. Benzene ring vibrations are found to make a major contribution in the IR and Raman spectra of the sample. Benzene ring stretching vibrations usually occur in the region 1580-1300 cm 129-30. For aromatic six-membered rings, e.g. benzene and pyridines, there are 2 or 3 bands in this region due to skeletal vibrations, the strongest usually being at about 1500 cm1. In the case where the ring is conjugated, a further mode at 1580 cm1 is also observed. For substituted benzene with identical atoms or groups on all para pairs of ring carbon atoms, the vibrations giving rise to the band at 1625-1590 cm1 are infrared inactive due to symmetry considerations, the compound having a center of symmetry at the ring center. If the groups in para positions of carbon atoms are different, then there is no center of symmetry and the vibrations are infrared active. 31. The ring CC stretching vibrations occur in the region 1650-1400 cm132. In the present work, the bands at 1604, 1583, 1504, 1246 cm1 in FTIR and the strong band at 1598 cm1, along with the above-mentioned weak band at 1292 cm1 in FT-Raman are assigned to CC stretching vibrations, staying in good agreement with the theoretically computed values at 1599, 1572, 1487, 1286, 1244 cm1. The calculated ring symmetric and asymmetric deformations may be probed by Raman spectroscopy. According to the theory, the symmetric modes may be found at 801 and as a strongly mixed mode at 344 cm1, while the asymmetric ones may be found at 650 and 307 cm1. It is experimentally confirmed by the presence of the bands at 798 and 338, 633 and 309 cm1 as well as with the literature values 33. The torsional deformations contribute significantly to the vibrations observed below 800 cm1. These bands were observed via FT-Raman's spectroscopy at 551 and 208 cm1, however the related modes are strongly mixed mainly with the out-of-plane deformations of the substituents. The theoretically predicted band at 709 cm1 corresponds to the Rodriguez torsional deformation. However, this mode was not observed experimentally due to the high intensity of near-laying .cs mode. 4.2.3 CH3 vibrations. The tidal molecule possesses 2 CH3 groups as shown in Fig.4. For the assignments of CH3 group frequencies, basically 9 fundamentals can be associated to each CH3 group, namely, the symmetrical stretching, asymmetrical stretching, the symmetrical, asymmetrical deformation modes, in-plane rocking, out-of-plane rocking, and twisting modes. The CH stretching modes in CH3 occur at lower frequencies than those of aromatic ring. In theory, the asymmetric CH stretching modes were found in the range 3009-2942 cm1 mode nose, 50 to 47, while the symmetric CH stretching modes at 2917 and 2885 cm1. These wave numbers are supported by the experimental bands found at 3016, 2934, 2853 cm1 in FTIR and 3013, 2936, 2856 cm1 in FT-Raman spectra, respectively. These assignments are also supported by the literature 34 in addition with the PET analysis. For methyl substituted benzene derivatives, the asymmetric and symmetric deformation vibration of the methyl group normally appear in the region 1465-1440 cm1 and 1390-1370 cm1 respectively. 35, 36, 37. The theoretically predicted frequency at 1325 cm1 mode No. 36 was assigned to symmetric deformation vibration of CH3 group and are in good agreement with the above literature data. The in-plane bending vibrations of the CH3 group have been identified theoretically at 1458 and 1447 cm1, staying in very good agreement with the experimental values found at 1445 cm1 and 1449 cm1 in the FT-IR and FT-Rs spectra, respectively. The out-of-plane bending vibration manifest in the experimental infrared spectrum as a band of medium intensity at 1470 cm1, staying in the excellent agreement with the theoretically predicted value of 1469 cm1. The rocking vibrations of CH3 mode usually appear in the region 1070-1010 cm138. The theoretically computed frequencies are spread over the range 1175-948 cm1. The upper energy vibrations correspond to the rocking modes of the methoxy group. The strong bands recorded at 1183, strong in FT-IR, and 1178 cm1, medium strong in FT-Rs, are linked to the out-of-plane methoxy rocking, 53% in PED, while the in-plane rocking vibration is assigned to the weak band observed via FT-IR at 1121 cm1. The weak band found at 972 cm1 in FT-IR has been assigned to SCH3 rocking vibrations. 4.2.4 CO and CS vibrations. The characteristic Alkazi group vibrations are CO stretching and CO bending vibrations. They are expected in the region 1140-395 cm1 and 1700-875 cm1 depending on the presence of specific interactions, whether monomeric, dimeric or other hydrogen-bonded species are present. 38. However, these bands overlap with other due to aromatic or aliphatic chain vibrations. Hence their undisputed assignment is often very difficult. 38. Here, it is clearly reflected in presented PED, where the vibrations involving Alkazi bridge reveal strongly coupled character. In our present investigation, the strong bands observed at 1246 Vs, and 1034 S, cm1 in FT-IR are assigned to CO stretching, being well supported by the theoretical values of 1231 and 1023 cm1 with the dominant contributions of .caro in PED equal 42 and 68%, respectively. The weak band observed at 1121 and 1183 cm1 in FT-IR and the one at 1178 cm1, corresponding to the latter in FT-Raman spectrum are assigned to OC3 in and out-of-plane bending, and they are all well supported by the theoretical and literature values. Most of the CS vibrations are manifested by the theory below 750 cm1. Being strongly mixed, the modes cannot be treated separately. However, the most characteristic band, related to the CS stretching, may be observed in Raman spectrum at 717 cm1. The band should be of weak intensity in infrared, however being of very strong intensity in Raman spectrum 39. The corresponding theoretical value differs significantly, giving the wave number of 672 cm1 with almost pure relation to the CS stretching coordinate with the PED contribution of 91%. All the tested theory levels brought similar fail in the prediction of the quoted frequency, however applying the set of scale factors defined by Krishnakumar et al. Leads to the closest value 694 cm1. It suggests that the fail may be due to a systematic error delivered by the selected level of theory. 4.3 Nmr Analysis. In Proton Nmr spectrum of the tidal compound, two signals at 2.41 and 3.72 ppm with each 3 protons integral are assigned to SCH3 and OC3 protons respectively. Likewise in aromatic region, oxygen adjacent 2 aryl protons are resonated as a singlet at 7.23 ppm with 2 protons integral, and sulfur adjacent protons appeared as a singlet at 6.89 ppm with 2 protons integral. This deshielding and shielding of aryl protons are due to the electronegativity of oxygen and sulfur atoms respectively. In 13 Cnmr spectrum, a less intense signal at 158.08 ppm is assigned to OC3 bearing ipso carbon, whereas two signals at 129.62 and 115.14 ppm are due to the oxygen attached to 2 aryl carbons and sulfur attached to aryl carbons respectively. In the upfield region, a signal at 55.54 ppm is assigned to OCT3 carbon and a signal at 17.13 ppm is attributed to SCH3 carbon. The molecular structure of the MTA molecule was optimized. Then, gauge including atomic orbital, GIAO, 13 Cnmr and 1H Nmr chemical shifts calculations of the 4-MTA molecule were carried out by using B3LYP functional with 6-311++ G, dp, basis sets. The Nmr spectra calculations were performed by using the Gaussian 0914 program package. The calculations reported were performed in DMSO solution using the IEF-PCM model, rather than in the gas phase, in agreement with experimental chemical shifts obtained in DMSO solution. The experimental and calculated values for 13C and 1H Nmr are shown in table point 4. The observed 1H and 13C Nmr spectra of 4-MTA is plotted in Fig. Point 5. 4.4 NBO analysis. Natural bond orbital analysis gives the most accurate possible natural Lewis structure picture of O because all orbitals are mathematically chosen to include the highest possible percentage of the ED. Interaction between both filled and virtual orbital spaces information is correctly explained by the NBO analysis, and it could enhance the analysis of intra- and intermolecular interactions. The second-order perturbation theory analysis of the Fock matrix was carried out to evaluate donor, I, acceptor, J, i.e. donor level bonds to acceptor level bonds interaction in the NBO analysis 40. The result of interaction is a loss of occupancy from the concentration of electron NBO of the idealized Lewis structure into an empty non-Lewis orbital. For each donor, I, and acceptor, J, the stabilization energy E, 2, associated with the delocalization I, J is estimated as 8. Where chi is the donor orbital occupancy, Ej, and Ei are diagonal elements, and F, I, J, is the off-diagonal NBO Fock matrix element. Natural bond orbital analysis provides an efficient method for studying intra- and intermolecular bonding and interaction among bonds, and also provides a convenient basis for investigating charge transfer or conjugative interaction in molecular systems. Some electron donor orbital, acceptor orbital, and the interacting stabilization energy resulting from the second-order microdisturbance theory are reported 41, 42. The larger E, 2, value, the more intensive is the interaction between electron donors and acceptor, i.e. the more donation tendency from electron donors to electron acceptors and the greater the extent of conjugation of the whole system 43. Delocalization of ED between occupied Lewis, type, bond or lone pair, NBO orbitals and formally unoccupied, anti-bond or Rydberg, non-Lewis NBO orbital correspond to a stabilizing donor-acceptor interaction. The charge transfer during the intermolecular interaction shows the delocalization of energy from one bond to another. The C1-C6 bond has S** and P** type electrons, and its densities are 1.9787 and 1.6750 respectively. The lower bond density shows more stabilization due to higher occupancies in acceptor bonds. It is evident that the transfers from C1-C6, C2-C3, and C4-C5 to its antibonding orbitals of C1-C2, C1-C2 and C3-C4 are 3.11, 3.49, and 3.58 kJ/mol respectively. When considering the p-bonds C1-C6, 2, C2-C3, 2, and C4-C5, 2, transfer more energy than S to its p** antibonding orbitals. The transition from PC1-C6 is about 21.26 and 17.82 kcal/mol to the C2-C3 and C4-C5 acceptor bonds. The other p bonds are PC2-C3, C4-C5 that transfer 18.61, C1-C6, 22.48, C4-C5, and 22.94, C1-C6, 18.53 kcal/mol, C2-C3, respectively. The lone pair atoms sulfur and oxygen are of higher electron density, and hence they are not able to have more hyperconjugative interaction energy. The E, 2, Values and types of the transition are shown in Table 0.5. 4.5 HOMO-LUMO analysis. The HOMO and the LUMO are very important parameters for quantum chemistry. We can determine the way the molecule interacts with other species, hence, they are called the frontier orbitals. HOMO, which can be thought the outermost orbital containing electrons, tends to transfer these electrons as an electron donor. On the other hand, LUMO can be thought as the innermost orbital containing free places to accept electrons 44. The HOMO and LUMO energy calculated by B3LYP/6-311/6-311 G, dP, and HF/6-311 G, dP, methods are shown in Table 0.6. This electronic transition absorption corresponds to the transition from the ground to the first excited state, and it is mainly described by an electron excitation from the HOMO to the LUMO. The HOMO is located over the SCH3 group, and the HOMO LUMO transition implies an electron density transfer to phenyl ring, which behaves as an acceptor. Energy gap of the frontier orbital has been found, and it reveals to be more stable since the shortest band gap is 0.20097 eV. The atomic compositions of the frontier molecular orbitals are shown in Fig. 0.6. The SCF energy of 4 MTA is -61.580. 4.6 Molecular electrostatic potential. The molecular electrostatic potential isosurface is superimposed onto the total electronic density. The value of the molecular electrostatic potential, V, R, created by a molecular system at a point R gives the electrostatic energy on a unit positive charge located at R. The MEP is a useful property to study reactivity, given that an approaching electrophile will be attracted to negative regions, particularly to the points with most negative values, where the electron distribution effect is dominant. Experimental V, R, computed with electron densities obtained from X-ray diffraction data has been used to explore the electrophilicity of hydrogen bonding functional groups 45. In the majority of the MEPs, while the maximum positive region, which is the preferred site for nucleophilic attack, is indicated with blue color, the maximum negative region, which is the preferred site for electrophilic attack, is indicated with red color. The study of experimental and theoretical V, R, shows that H donor and H acceptor properties of molecules are revealed by positive and negative regions, respectively, so that the formation of an H bond can be regarded as the consequence of a complementarity between the electrostatic potentials 45. In the present study, the molecular electrostatic potential of 4 MTA is calculated using B3LYP/6-311 G, dP, method and is depicted in Fig. 0.7. Negative regions are associated with oxygen and sulfur atoms. These are expected to be the most preferred region for electrophilic attack. However, the maximum positive region is localized on carbon and hydrogen. Therefore, it would be predicted that it is the preferred site for nucleophilic attack. 4.7 Other molecular properties. 4.7.1 Mulliken charges. The calculation of atomic charges plays an important role in the application of quantum mechanical calculations to molecular systems 46. The charge distributions calculated by the Mulliken 47 and NBO methods for the equilibrium geometry of 4 MTA is given in Table 0.7. The charge distribution on the molecule has an important influence on the vibrational spectra. The corresponding Mulliken's plot is shown in Fig. 0.8. In 4 MTA, the Mulliken atomic charge of C3 in B3LYP/6-311 G, dP, shows positive value while it is negative both in HF and NBO. C12 possesses more negative charge because the highest electron occupied level is over the SCH3 group. Hence it behaves as an electron donor. Since C1 behaves as an acceptor, it possesses more positive charge. 4.8.1 Thermodynamic Properties. The calculated thermodynamic parameters are presented in the Table 0.8. Scale factors have been recommended 48 for an accurate prediction in determining the zero-point vibrational energies and the entropy S. The variation in the zero-point vibrational energies seems to be insignificant. The total energies were found to decrease with increase of the basis sets. The changes in the total entropy of 4 MTA at room temperature at different basis sets are only marginal. 5. Conclusion. In this work, 4 MTA has been characterized by Nmr, FT-IR, FT-Raman, HOMOLUMO, and NBO analysis. The energies, geometrical parameters, vibrational frequencies, and 13C/1H chemical shift values of the tidal compound were calculated using ab initio and DFT/B3LYP at the several basis set levels. Correlations between the proton and 13C experimental chemical shifts and the GIAO Nmr calculations are found to be in good agreement. The molecular electrostatic potential of 4 MTA reveals the most preferred region for electrophilic attack, and it is found to be over the negative regions associated with oxygen and sulfur atoms. In addition, the thermodynamic, Mulliken charges, nonlinear optical, total dipole moment and first-order hyperpolarizabilities properties of the compound have been calculated in order to get an insight into the compound. Acknowledgements. The computations were partially done by K. Druzbicki at the Academic Computer Center Cyfernet, Krakow, Poland. Grant number, MNISW/SGI3700/UJ/007/2009. Our hearty thanks also goes to Yusuf Erdogdu, Department of Physics, Faculty of Arts and Science, Ahi Evran University, Kırşehir, Turkey, and Tom Sundias, Department of Physics, University of Helsinki, Fin 00014, Finland, for timely help and constant support in completion of this work.